Picture this: a ghostly, luminous triangle rising from the horizon just after sunset or before dawn, faint but unmistakable, stretching upward into the dark canvas of the night sky. This isn't a trick of the eye or some fleeting atmospheric illusion. It's the zodiacal lights, one of the most enigmatic and mesmerizing phenomena in our solar system. For centuries, this ethereal glow has captivated astronomers, poets, and stargazers alike, sparking questions that linger even today. What creates this celestial spectacle? Why does it appear only under certain conditions? And what secrets might it hold about the hidden workings of our cosmic neighborhood? The truth is, the zodiacal lights aren't just a beautiful accident of nature, they're a cosmic puzzle wrapped in layers of mystery. Ancient civilizations mistook them for the breath of the gods or the echoes of distant fires. Even modern science, with all its advanced tools and telescopes, still grapples with unanswered questions about their origins. Some theories suggest their sunlight reflecting off vast clouds of dust particles drifting between the planets. Others propose more exotic explanations, like remnants of long-dead comets or even clues to undiscovered worlds lurking in the shadows. But one thing's certain: the zodiacal lights are more than just a pretty sight. They're a window into the untold stories of our solar system's past and future. In this video, we're diving deep into the 25 greatest mysteries surrounding this haunting glow. From the bizarre behavior of interplanetary dust to the possibility of hidden asteroid belts, each clue we uncover pulls us deeper into a web of cosmic intrigue. You'll discover how something so delicate and faint could hold the key to understanding everything from the birth of planets to the fate of our own celestial backyard. So if you've ever looked up at the night sky and wondered what secrets it's keeping, you're about to embark on a journey that'll change the way you see those shimmering lights forever. This isn't just astronomy, it's a detective story written in starlight. The zodiacal lights might look like a soft, misplaced sunrise or sunset, an eerie glow hovering just above the horizon long after the sun has disappeared or before it rises. But this isn't sunlight scattering through Earth's atmosphere. It's something far more cosmic. Imagine billions upon billions of tiny dust particles, each no larger than a grain of sand, floating in the vast emptiness between planets. When sunlight hits these particles, they scatter its rays, creating that faint, mystical triangle of illumination stretching upward along the path of the ecliptic, the same plane where our moon and planets travel across the sky. Ancient skywatchers didn't have telescopes or satellites to explain what they were seeing, so they wove myths around this celestial mystery. The Babylonians saw it as a heavenly ladder. The Greeks called it the false dawn, believing it was the glow of unseen fires beyond the horizon. Even today, in some cultures, it's considered a bridge between the earthly and the divine. But science tells a different story, one that's just as fascinating. These lights are essentially sunlight bouncing off interplanetary dust, a cosmic echo of our solar system's turbulent past. What makes them so elusive? They appear only under the darkest, clearest skies, away from city lights and atmospheric pollution. And because they align with the ecliptic, they're most visible near the equator, where the plane of our solar system stands almost vertical in the sky. That's why travelers to remote deserts or tropical islands sometimes catch this ghostly radiance when the conditions are just right. But even with all our modern tools, we're still piecing together where all that dust comes from. Is it debris from colliding asteroids, the remains of vaporized comets, or something even stranger? The answers might just rewrite what we think we know about the silent, drifting history of our solar system. The most widely accepted explanation for the zodiacal lights points to something so small it's almost invisible: dust. Not just any dust, but a vast, diffuse cloud of microscopic particles stretching throughout the inner solar system, centered along the same flat plane where Earth and the other planets orbit the Sun. Scientists call this the dust cloud hypothesis, and it suggests that when sunlight hits these tiny fragments, they scatter its glow like billions of miniature mirrors, creating that eerie luminous triangle we see from Earth. But where does all this cosmic dust come from? One major source lies in the asteroid belt, that ring of rocky debris between Mars and Jupiter. When asteroids collide, and they do, often violently, they don't just shatter into large chunks. The impacts generate countless fine particles, some no bigger than a speck of flour, which then drift inward toward the Sun over thousands of years, another contributor. Comets, as these icy wanderers swing close to the Sun, their frozen surfaces vaporize, releasing not just spectacular tails, but also trails of dust that linger long after the comet itself has moved on. Over time, this debris spreads out along the comet's orbital path, adding to the solar system's dusty reservoir. Yet there's a problem with this seemingly straightforward explanation. If the zodiacal dust comes mostly from asteroids and comets, why does its distribution appear smoother and more uniform than we'd expect? Collisions and comet tails should create clumps and variations in density, but the glow of the zodiacal lights is remarkably even. That inconsistency has led some researchers to propose even wilder possibilities, like the idea that a significant portion of this dust might actually be interstellar in origin, drifting into our solar system from the void between stars. Others wonder if we're underestimating the role of smaller, unseen objects, like undiscovered families of microasteroids or even the remnants of ancient planetary collisions. The dust cloud hypothesis isn't just about solving a celestial light show. It's a way to trace the hidden history of our solar system. Every speck of that interplanetary debris carries clues, chemical signatures, orbital patterns, even hints about events that happened billions of years ago. By studying the zodiacal lights, we're essentially sifting through cosmic archaeology, piecing together the long-forgotten collisions and disruptions that shape the space around us. And as our tools improve, from high-altitude observatories to space-based dust detectors, we're getting closer to reading that story in the faint glow of sunlight on ancient dust. If dust from asteroids and comets fills the inner solar system, why doesn't it spread out smoothly like powder sprinkled on a table? Instead, the zodiacal dust behaves strangely, clustering closer to the Sun, thinning out near planets and even leaving mysterious gaps in its distribution. This uneven scattering defies simple explanations, revealing a hidden dance of gravity and celestial mechanics at work. Take Mercury, for example. The tiny planet orbits so close to the Sun that its gravity acts like a cosmic broom, sweeping dust particles out of its path. Over millennia, this creates a noticeable void in the dust cloud along Mercury's orbit. Larger planets like Jupiter, with their immense gravitational pull, carve out even bigger gaps by flinging dust away or trapping it in resonant orbits, places where particles circle the Sun in sync with the planet's own rhythm, like two pendulums swinging in perfect time. These gravitational nudges don't just clear space, they sculpt the dust into intricate patterns like invisible rivers flowing through the solar system. But gravity isn't the only force at play. Solar radiation exerts its own subtle pressure, gently pushing smaller dust grains toward the Sun while larger ones lag behind. This creates a surprising density gradient, thicker dust clouds near the Sun's furnace, fading to wisps farther out. Some scientists argue that this imbalance might even hint at undiscovered phenomena, like micrometeoroid showers from hypothetical asteroid families or the ghostly remnants of long-vanished protoplanets. The most puzzling gaps, though, appear where theory says they shouldn't. Near Earth's orbit, for instance, there's less dust than models predict. One daring hypothesis suggests our own planet might be responsible, its gravity funneling dust into temporary rings that eventually spiral into the atmosphere, like a hidden rain of cosmic debris we never noticed. Others speculate that electromagnetic forces stirred by the Sun's magnetic field could be herding particles into invisible structures. What makes these dust patterns so fascinating isn't just their strangeness, it's what they reveal about the solar system's hidden architecture. Every gap and cluster acts like a fingerprint, marking the gravitational hands that shaped it. By mapping these irregularities, astronomers aren't just solving a riddle about light in the sky. They're piecing together a dynamic, ever-changing portrait of how celestial bodies interact in the dark. And with every new discovery, from resonant dust rings to solar wind-driven currents, the zodiacal lights become less of a mystery and more of a mirror, reflecting the invisible forces that have sculpted our cosmic neighborhood for billions of years. Jupiter isn't just the solar system's largest planet. It's a gravitational titan, a cosmic sculptor whose influence stretches far beyond its own orbit. And when it comes to the zodiacal dust cloud, Jupiter's pull might be the hidden hand shaping its most puzzling asymmetries. Picture this: a planet so massive that its gravity can fling asteroids into the sun, sling comets into deep space, and even warp the delicate distribution of dust across the inner solar system. Scientists have long suspected that Jupiter's sheer weight plays a key role in why the zodiacal lights don't glow uniformly, why some regions appear brighter or dimmer than simple models predict. One of the clearest signs of Jupiter's influence lies in something called orbital resonance. Just as pushing a child on a swing at just the right moment amplifies their motion, Jupiter's gravity tugs on dust particles in rhythm with their orbits, creating zones where debris either piles up or gets cleared out. Particles that orbit the Sun, say, twice for every one of Jupiter's trips around, might find themselves herded into dense rings or ejected entirely. This creates a patchwork of bright and dark bands in the dust cloud, invisible to the naked eye but detectable through careful observation of the zodiacal light's subtle variations. But Jupiter's impact goes beyond mere resonance. Its gravity also acts like a cosmic sieve, sorting dust by size. Larger grains, less affected by solar radiation, tend to linger in stable orbits. Meanwhile, smaller particles, those easily pushed by sunlight, get scattered into eccentric paths, some funneled toward the sun, others tossed outward like confetti. This sorting effect could explain why the zodiacal glow appears smoother in some wavelengths and clumpier in others, a fingerprint of Jupiter's invisible hand rearranging the solar system's debris. Perhaps most intriguing is the possibility that Jupiter's gravity doesn't just shape the dust cloud, it might also supply it. The planet's Trojan asteroids, two vast swarms of rocks trapped in its orbital wake, are known to collide occasionally, generating fresh dust that could seep inward over time. Even more speculative is the idea that Jupiter's gravitational jostling might nudge other asteroids or comets into collision courses, indirectly seeding the zodiacal cloud with new material. Yet for all we've pieced together, Jupiter's full role remains a mystery. Some models suggest its influence should be even stronger, that the dust cloud ought to show more extreme gaps or concentrations than we observe. Others argue that without Jupiter, the zodiacal light might not exist at all, its glow smeared into a featureless haze by unchecked chaos. The deeper we look, the more Jupiter reveals itself as both architect and disruptor, a force that doesn't just shape the dust but actively rewrites the rules of its dance. And as we study those rules, we're not just solving a puzzle about light in the sky, we're learning how the solar system's mightiest planet quietly orchestrates the motion of matter too small to see. Here's something that doesn't add up despite all the asteroids, comets, and cosmic collisions constantly feeding dust into the inner solar system. The amount of zodiacal dust we actually observe is far less than what calculations predict. It's as if someone left the solar system's back door open, letting a steady stream of particles slip silently away. Scientists call this the missing dust problem, and it's one of the most puzzling gaps in our understanding of the zodiacal lights. If the dust cloud should be far denser than it appears, where is everything going? One leading suspect is a phenomenon called pointing Robertson drag. Picture a tiny dust grain orbiting the sun, As it moves, it absorbs sunlight and re-emits that energy in all directions. But because the particle is moving forward in its orbit, the light it emits gets slightly pushed backward, like a runner tossing a ball behind them. This creates a minuscule but relentless drag force, slowing the particle down over time. The effect is incredibly subtle, like a single grain of sand feeling the gentle tug of a breeze. But across millions of years, it's enough to spiral dust grains inward toward the sun, where they eventually vaporize. Pointing Robertson drag could explain why we don't see as much dust as expected. It's constantly being drained away, particle by particle, into the sun's fiery embrace. But there's another force at work, the solar wind. This stream of charged particles blasting from the sun doesn't just create auroras, it also exerts pressure on interplanetary dust. Smaller grains, especially those with electric charges, can get caught in this flow like leaves in a river, swept outward or pushed off course. Some researchers suggest that over time, this could scatter dust into wider orbits or even eject it from the inner solar system entirely, thinning out the cloud more than models account for. Then there's the possibility of hidden sinks, places where dust accumulates without us realizing. Earth itself might be one. Our planet's gravity pulls in thousands of tons of cosmic dust annually, some of it settling through the atmosphere as micrometeorites. Other planets like Venus or Mars could also be vacuuming up debris, though on smaller scales. Even collisions between dust grains might play a role, grinding particles down to sizes so small they become invisible to our instruments or susceptible to other forces like solar radiation pressure. The most tantalizing theory, though, involves something far more dramatic. The idea that past cosmic cataclysms might have temporarily flooded the solar system with dust, leaving behind an overabundance that's still slowly dissipating. Imagine an asteroid collision so violent it unleashed a dust storm larger than anything seen in modern times, or a comet disintegrating so completely it left a lingering haze. Over millennia, pointing Robertson drag and solar wind would have whittled that excess away, leaving us with the thinner cloud we see today. The missing dust problem isn't just about accounting for lost particles, it's a clue to the dynamic balance of forces shaping our solar system. Every grain that vanishes tells a story, whether it's spiraling into the sun, drifting into interstellar space, or settling silently onto a distant world. And as we piece together where the dust goes, we're not just solving a celestial accounting error. We're uncovering the hidden rhythms of gravity, light, and time that govern the unseen rubble of our cosmic neighborhood. One of the most striking things about the zodiacal lights isn't just their ghostly presence, it's how their color seems to shift before our eyes. Low on the horizon, they often take on a warm, reddish hue like the last embers of sunset. But as your gaze follows the glow upward, that tint fades into a cooler, almost whitish radiance. This isn't just a trick of perception, it's a clue to the complex interplay of sunlight, dust, and Earth's own atmosphere. The reddish glow near the horizon comes down to a phenomenon we're all familiar with, even if we don't realize it: Rayleigh scattering. This is the same effect that turns our sky blue at noon and paints it red at dawn and dusk. When sunlight passes through the thickest part of Earth's atmosphere near the horizon, air molecules scatter shorter blue and green wavelengths out of the beam, leaving behind the longer red and orange wavelengths to dominate. The zodiacal light, being sunlight reflected off dust, gets filtered through this same atmospheric lens, taking on those warm tones as it grazes the horizon. But higher in the sky, where the light travels through less atmosphere, that filtering effect weakens. Here, the zodiacal glow appears closer to its true color, a pale, nearly neutral white. That's because interplanetary dust doesn't absorb or scatter sunlight in any one particular direction or wavelength the way our atmosphere does. Instead, it reflects sunlight more or less uniformly, producing a glow that's essentially a diluted version of the sun's own light. But there's a twist. Some observers report subtle color variations that can't be explained by atmospheric effects alone. under exceptionally clear, dark skies, the highest reaches of the zodiacal light sometimes show a faint yellowish or even greenish tinge. This might hint at the actual composition of the dust itself. Certain minerals like silicates or metallic oxides could scatter sunlight in slightly different ways, adding a barely perceptible tint to the glow. Iron-rich particles, for instance, might nudge the reflected light toward warmer tones, while icy or carbon-based grains could skew it cooler. Even more intriguing is the possibility that these color variations could map the dust's origins. Cometary dust, rich in volatile ices and organic compounds, might scatter light differently than the rocky debris left behind by asteroid collisions. If we could measure these subtle color shifts precisely enough, we might be able to trace which parts of the zodiacal cloud come from which parent bodies, like reading a cosmic fingerprint in gradients of pale light. Of course, teasing out these details isn't easy. Human eyes aren't the most reliable instruments for judging faint colors in near darkness, and even cameras can struggle to capture the zodiacal light's true hues without over-amplifying noise. That's why scientists turn to spectrographs, breaking the glow into its component wavelengths to analyze its chemical signatures indirectly. What they've found so far only deepens the mystery. The dust's reflectance properties don't quite match any known asteroid or comet type perfectly, suggesting we're still missing pieces of the puzzle. The zodiacal light's shifting colors are more than just a visual curiosity. They're a silent dialogue between sunlight and the cosmos, a way to decode the hidden nature of the dust that fills our solar system. Every tint and tone carries information about Earth's atmosphere, about the dust's journey, even about events that happened long before humans first looked up and wondered at that faint, eerie glow in the pre-dawn sky. Even the most dedicated stargazers often miss it, a faint, elusive patch of light glowing directly opposite the sun in the night sky, so subtle it vanishes with even a hint of light pollution. This is the Gegenschein, German for counterglow, one of the most mysterious and least understood features of the zodiacal light family. Unlike the familiar triangular glow near the horizon, the Gegenschein appears as a dim, circular bright spot, barely distinguishable from the backdrop of stars. Some scientists argue it's just another facet of the zodiacal phenomenon, sunlight reflecting off interplanetary dust, but others insist its unique behavior hints at something far stranger, a cosmic anomaly with rules of its own. What makes the Gegenschein so puzzling is its perfect alignment. It always sits exactly 180 degrees from the sun, like a ghostly echo in the midnight sky. While the zodiacal light stretches along the ecliptic, the Gegenschein concentrates into a discrete, localized glow. This precise positioning suggests something more than random dust scattering. It implies a geometric perfection, as if sunlight is bouncing off particles arranged in a way we don't yet understand. One theory points to orbital resonance, where dust grains cluster at this antisolar point due to gravitational equilibrium. Another proposes that these particles might be preferentially oriented, their flat surfaces acting like microscopic mirrors, all angled to reflect sunlight back toward Earth. Yet the Gegenschein's behavior defies simple explanations. During certain times of the year, particularly around March and September, it brightens noticeably, as if something invisible is funneling extra dust into this celestial hotspot. Even more perplexing, spacecraft like the Pioneer missions have detected faint dust concentrations at this antisolar point, but not enough to account for the Gegenschein's glow. Some researchers speculate that electrostatic forces might play a role. Tiny dust grains charged by solar radiation could align themselves into loose, reflective structures, amplifying the effect. Others wonder if we're seeing the shadow of Earth itself, with our planet's gravity subtly sculpting the dust cloud into a denser patch opposite the sun. Then there's the debate over whether the Gegenschein is truly part of the zodiacal light at all. Traditional models treat it as just another angle of the same dusty disk, but its crisp boundaries and inconsistent intensity suggest it might be a distinct phenomenon. Some astronomers point to the glory effect, a rare optical phenomenon where backscattered light creates a bright ring around a shadow, except here, there's no solid object casting that shadow, just the emptiness of space. Could the Gegenschein be sunlight interacting with an undiscovered population of nanoparticles, or even the lingering traces of a long-gone comet's tail? What's certain is that the Gegenschein refuses to fit neatly into our cosmic categories. It's a reminder that even the faintest glimmers in the night sky can hold profound secrets, clues to forces and structures we're only beginning to imagine. And until we send probes deep enough into the solar system's dust clouds to measure their structure directly, this counterglow will remain both a footnote to the zodiacal lights and a tantalizing mystery of its own. The zodiacal lights don't appear with the same brilliance every night. There are times of the year when they blaze across the sky like a celestial beacon, and others when they all but vanish into the darkness. This isn't random chance, it's a cosmic dance between Earth's tilt and the precise geometry of our solar system. Imagine standing on a planet whose axis leans at 23.5 degrees, orbiting a sun surrounded by a flat, dusty disk. Depending on where Earth is in its yearly journey, that disk, the plane of the ecliptic, will rise at different angles relative to our horizon, and that angle makes all the difference. Around the equinoxes in March and September, something extraordinary happens. The ecliptic arcs steeply upward from the horizon after sunset or before sunrise, almost perpendicular to the ground. This steep angle means the zodiacal light isn't diluted by the thick, hazy layers of Earth's atmosphere near the horizon. Instead, it shoots upward through clearer, thinner air, appearing brighter and more defined. It's like holding a flashlight straight up into a dark room. The beam stays concentrated and intense. This is why spring and autumn are prime seasons for spotting the zodiacal glow, especially in temperate latitudes where the ecliptic's tilt aligns perfectly with the twilight sky. But travel closer to the equator and the rules change. Here, the ecliptic always rises nearly vertically, making the zodiacal light visible year-round, though even then it waxes and wanes in intensity based on Earth's position. Near the poles, however, the situation flips. During summer or winter, the ecliptic hugs the horizon so tightly that the zodiacal light gets smeared into invisibility, drowned by the lingering glow of twilight or the sun's perpetual presence. Only during brief windows near the equinoxes do polar observers catch fleeting glimpses of it, and even then, it's often too faint to discern. There's another layer to this seasonal puzzle, the varying length of twilight. In summer, especially at higher latitudes, twilight drags on for hours, leaving the sky too bright for the delicate zodiacal glow to compete. Winter, on the other hand, offers shorter, sharper transitions between day and night, but the ecliptic's shallow angle often stifles the light's visibility anyway. This creates a narrow sweet spot, a handful of weeks around the equinoxes when darkness falls fast, and the ecliptic stands tall, framing the zodiacal light in perfect clarity. Yet even these patterns aren't universal. Local conditions like pollution, atmospheric dust, even humidity can amplify or erase the zodiacal light's visibility regardless of season. High-altitude deserts with their thin, dry air and pitch-black skies might reveal the glow even when geometry says it should be faint. Meanwhile, urban observers might miss it entirely, no matter how perfectly aligned the ecliptic. What makes these seasonal shifts so fascinating isn't just their predictability, it's how they mirror the grand choreography of our solar system. The zodiacal light isn't just a static feature, it's a dynamic response to Earth's perpetual motion, a reminder that even the faintest glows in our sky are tied to the rhythms of planets' orbits and axial tilts. And for those who learn its schedule, the reward is a front-row seat to one of the cosmos' most subtle and elegant performances. The same dust that creates the ethereal glow of the zodiacal lights is also responsible for one of the night sky's most dazzling displays, meteor showers. On any given night, Earth plows through this cosmic debris at speeds of tens of thousands of miles per hour, turning specks of interplanetary dust into streaks of luminous fire. But during certain times of the year, our planet crosses paths with denser ribbons of debris, remnants of comets or shattered asteroids that transform quiet skies into meteor storms. What's fascinating is that these events aren't just isolated spectacles, they're glimpses into the very heart of the zodiacal dust cloud, revealing its clumps, voids, and hidden reservoirs. Take the Perseids, one of the most reliable meteor showers. Every August, Earth barrels through the debris trail of comet Swift-Tuttle, a miles-wide ball of ice and rock that last passed near the Sun in 1992. As our planet collides with particles no larger than grains of sand, friction with the upper atmosphere heats them to thousands of degrees, vaporizing them in flashes of light we see as shooting stars. But here's the twist: the zodiacal light often grows slightly more intense around these meteor showers, as if the same dust feeding the meteors is also thickening the background glow. That's because meteor showers aren't just isolated streams, they're part of a vast, uneven tapestry of dust with denser threads woven into the broader cloud. This connection goes even deeper. Some meteor showers, like the Geminids in December, don't come from comets at all. Instead, they originate from an asteroid 320 Phaethon, a rocky body that behaves like a comet, shedding dust as it orbits the Sun. When Earth passes through Phaethon's debris trail, the zodiacal light near the Geminid radiant can appear subtly enhanced, a clue that this isn't just a random meteor swarm but a structured filament within the larger dust cloud. Scientists have even detected faint meteoroid streams, lingering along these paths, narrow rivers of particles too sparse to create visible meteors but dense enough to amplify the zodiacal glow. Yet not all debris fields behave the same way. Some comets, like Halley's, leave behind broad, diffuse trails that produce steadier but less intense meteor showers like the Orionids. Others, like Comet 55 Tempel-Tuttle, create narrow, concentrated streams responsible for storms like the Leonids, which can unleash hundreds of meteors per hour. These variations hint at the zodiacal dust cloud's complex anatomy, some regions smooth and well-mixed, others knotted with the remains of ancient cosmic collisions. The real mystery lies in the outliers. Every now and then, meteor showers flare brighter than expected, or the zodiacal light pulses with unusual intensity, suggesting Earth has grazed a previously unknown pocket of dust. Some researchers speculate these could be traces of long-dead comets, their orbits decayed into oblivion but their debris still lingering. Others wonder if planetary alignments, like Jupiter's gravity nudging a dust stream closer to Earth, might be unlocking hidden veins of material. What ties it all together is motion. The zodiacal dust cloud isn't static. It breathes and shifts, sculpted by gravity, sunlight, and the wakes of passing comets. Meteor showers are just the most visible ripples in this cosmic pond, fleeting signs of a much grander process, the slow, perpetual recycling of dust across the solar system. And when you stand under a meteor shower, you're not just watching debris burn up. You're witnessing the same celestial machinery that paints the zodiacal lights across the pre-dawn sky. Our solar system's zodiacal dust cloud might feel like a local phenomenon, an accident of celestial history unique to our cosmic backyard. But what if it's actually part of a universal pattern? Astronomers studying distant star systems have spotted similar halos of debris around young and mature stars alike, suggesting these dusty veils might be as fundamental to planetary systems as planets themselves. The question isn't just whether other stars have zodiacal equivalents, it's what these halos reveal about the life cycles of worlds, from their violent births to their slow, dusty declines. Take Beta Pictoris, a star just 60 light-years away. Hubble and other telescopes have captured stunning images of a vast, flat debris disk encircling it, a structure so pronounced it casts visible shadows across starlight. At first glance, it looks like our zodiacal cloud scaled up, a brilliant band of dust fed by colliding asteroids and evaporating comets, but there's a key difference. Beta Pictoris's disk is a chaotic adolescent compared to our solar system's middle-aged haze. Its dust grains are larger, its collisions more violent, and its structure warped by the gravitational tug of a massive planet, Beta Pictoris b, carving gaps like a ship plowing through celestial silt. This isn't just a zodiacal light, it's a snapshot of what our own system might have looked like 4 billion years ago, when planets were still bullying debris into submission. Then there's Fomalhaut, another star with a debris disk so vast it's visible to amateur telescopes. Here, the dust forms a lopsided ring, dense on one side and wispy on the other, a signpost of past planetary migrations or the gravitational wake of unseen worlds. Unlike our zodiacal cloud, which is relatively smooth, Fomalhaut's disk is riddled with clumps and strands, suggesting turbulent, ongoing collisions. Some researchers even speculate that its asymmetries could be debris from a cataclysmic asteroid impact, an event so violent it would make the dinosaur-killing Chicxulub impact look like a pebble drop. But not all dusty halos are young and chaotic. Around older stars like Vega, astronomers find thinner, more diffuse disks, remnants of planetary systems that have settled into something resembling our own. These disks glow faintly in infrared, their dust grains finer and more evenly distributed, much like the particles fueling our zodiacal light. Could these be the quiet twilight of once active systems, their asteroid belts ground down over eons, their comets spent? If so, our solar system might be midway through this life cycle, no longer the riot of Beta Pictoris, not yet the fading ember of Vega. The real surprise came when scientists began cataloging these extrasolar dust clouds. Nearly every star they examined, whether young or old, solitary or part of a binary system, had some detectable debris. Even TRAPPIST-1, the ultra-cool dwarf star with its 7 Earth-sized planets, shows hints of a tenuous dust ring. This ubiquity suggests that zodiacal-like clouds aren't anomalies, they're cosmic constants, natural byproducts of planet formation and evolution. Dust seems to be the universe's way of marking where planets once formed, where they still collide, or where they've left skeletons of their building blocks behind. Yet there's a lingering mystery. Some stars have dust halos far denser than anything in our solar system, while others are nearly pristine. Why the variation? One theory points to the role of giant planets like Jupiter. In systems where these gravitational gatekeepers are absent or poorly positioned, dust might spiral inward unchecked, piling up near the star or blowing away entirely. In others, planets could shepherd debris into dense rings or resonant bands, amplifying the halo's glow. Our own zodiacal light might owe its subtlety to Jupiter's quiet policing, its gravity siphoning dust away before it can accumulate into something brighter. The most tantalizing possibility is that these halos could hide clues to life itself. Dust isn't just inert grit, it carries water, ice, organic molecules, even prebiotic chemicals. In younger systems, thick debris disks might shield fledgling planets from harsh stellar radiation, while in older ones they could deliver the raw materials for life's chemistry. Our zodiacal cloud, faint as it is, might still sprinkle Earth with a slow rain of cosmic ingredients, the same way earlier dust showers may have seeded our planet's oceans. Studying these distant halos does more than satisfy curiosity. It holds up a mirror to our solar system's past and future. Every disk we find is a time capsule, a glimpse into how planetary systems are born, evolve, and fade. And as we piece together their stories, we're left wondering, is our zodiacal light just one verse in a galactic chorus sung by countless stars across the darkness? The answer could redefine not just what's normal in the cosmos, but how special or ordinary our own dusty corner of space truly is. Head to the Arctic or Antarctic and you'll notice something strange, or rather, the absence of something. The zodiacal light, so vivid near the equator and temperate zones, practically vanishes at the highest latitudes. It's not that the dust cloud disappears, it's that Earth's tilt and the geometry of our solar system conspire to hide it from polar viewers. This vanishing act reveals just how delicately the zodiacal glow depends on the angle between sunlight, dust, and the observer's vantage point. Near the poles, the ecliptic, the flat plane where planets and dust orbit the sun, skims almost parallel to the horizon. Imagine holding a dinner plate flat against a wall. From directly opposite, you'd barely see its edge. That's the challenge for polar observers. The zodiacal light spreads along the ecliptic, so when that plane hugs the horizon, its glow gets compressed into a thin, nearly invisible band, drowned by twilight or the sun's lingering glare. Even during polar night, when the sun stays below the horizon for months, the ecliptic's shallow angle means the zodiacal light stretches horizontally, blending into the diffuse glow of the Milky Way or auroras. Dust density plays a role too. While the inner solar system's dust cloud is thickest near the sun, it thins dramatically farther out. At Earth's distance, there's already less dust than near Mercury or Venus, but near the poles, the geometry exacerbates the problem. Dust particles tend to concentrate along the ecliptic plane, leaving the regions above and below it relatively sparse. When viewing from high latitudes, you're looking through the thinner top or bottom of this disk, where fewer particles mean fainter scattering. But there's another twist: atmospheric interference. Near the poles, the zodiacal light's already dim glow must travel through more of Earth's atmosphere at a low angle, passing through layers of ice crystals, haze, and temperature inversions that scatter and absorb its light. This is why, even during clear polar nights, the zodiacal glow often dissolves into the background, outshone by air glow or the shimmering curtains of the auroras. Interestingly, spacecraft tell a different story. Satellites orbiting above Earth's poles have detected the zodiacal light signature just fine, proof that the dust cloud is still there, uniform and unchanging. It's our ground-based perspective that warps it into invisibility. This disconnect hints at how much our understanding of cosmic phenomena depends on where we stand, or in this case, how tilted our planet happens to be. The poles aren't entirely devoid of zodiacal phenomena, though. On rare occasions, when the ecliptic tilts just right during equinoxes, a faint pillar of light might appear for fleeting moments. Some polar explorers have reported seeing a smudged, vertical version of the zodiacal glow, like a ghostly cousin to the more familiar triangular shape. These sightings are so rare they border on legend, but they underscore a key truth. The zodiacal light isn't gone at high latitudes, it's simply waiting for the perfect alignment of cosmic geometry and atmospheric clarity to reveal itself. This polar vanishing act isn't just a curiosity, it's a lesson in perspective. The same dust that paints brilliant skies near the equator fades to nothing near the poles, not because the universe changes, but because our view of it does. And that's a reminder worth carrying beyond astronomy sometimes. The most profound mysteries aren't about what's missing, but about how we're looking. Infrared astronomy has peeled back another layer of the zodiacal light's mystery, revealing a hidden thermal fingerprint that challenges everything we thought we knew about this cosmic glow. While our eyes see it as a pale, ghostly triangle, infrared telescopes detect something far more dynamic, a dust cloud pulsing with temperature gradients, hotter near the sun and cooling as it stretches outward. This thermal map isn't just a curiosity, it's a Rosetta Stone for decoding how dust behaves across the solar system and why the zodiacal light shines the way it does. At the heart of this discovery is a simple but profound truth. Dust doesn't just reflect sunlight, it absorbs and re-emits it as heat. Close to the sun, where temperatures soar, particles bake at hundreds of degrees, glowing fiercely in infrared. Farther out, beyond Earth's orbit, the same grains chill to near absolute zero, their thermal emissions fading into the background. Spacecraft like NASA Spitzer and the European Space Agency's Herschel have mapped this gradient in stunning detail, showing how the zodiacal dust cloud isn't uniform but a thermal tapestry threaded with warmth and cold. What's surprising is how dramatically temperature affects visibility. Near the sun, where dust is hottest, it doesn't just glow in infrared, it also scatters visible light more intensely, amplifying the zodiacal light's brightness. But there's a catch. These same particles are spiraling inward, doomed to vaporize in the solar furnace. Meanwhile, cooler dust in the outer regions lingers for millennia, its faint contributions to the zodiacal glow diluted by distance and frigid temperatures. This creates a paradox. The dust most responsible for the zodiacal light is also the most ephemeral, while the stable, long-lasting particles contribute the least. The infrared data also exposes odd inconsistencies. Some regions of the dust cloud radiate more heat than their particle density should allow, as if something, perhaps electrostatic forces or residual comet ices, is boosting their thermal output. Other zones appear unnaturally cool, suggesting shadowed reservoirs of dust shielded from direct sunlight. Most puzzling are the so-called thermal knots, localized patches where temperatures spike unpredictably, like cosmic hotspots with no obvious source. One theory points to microscopic collisions, dust grains smashing together at high speeds, briefly flash heating their surfaces. Another proposes that these knots could be trails of superheated debris left by undiscovered microasteroids, their orbits carrying them through denser dust lanes. Then there's the role of composition. Not all dust grains heat equally. Metallic particles, like those rich in iron or nickel, absorb sunlight efficiently, warming quickly and radiating strongly in infrared. Silicate grains, on the other hand, take longer to heat and cool, creating lagging thermal signatures that don't always align with visible light observations. This mismatch might explain why some portions of the zodiacal light appear brighter or fainter than infrared models predict. The dust's chemical makeup is subtly altering its thermal and optical behavior. Perhaps most intriguing is what these infrared observations reveal about the dust's origins. Cometary debris laced with volatile ices should heat and cool differently than rocky asteroid fragments. By analyzing thermal patterns, scientists have tentatively traced some zodiacal dust streams back to specific comet families, like the Kreutz Sungrazers or Encke's debris trail. Other thermal signatures hint at asteroid collisions in the distant past, their debris still glowing faintly from events that predate human civilization. The zodiacal light's infrared signature isn't just a side note. It's a hidden language of heat and motion, a way to see the invisible forces sculpting our solar system's dust. Every temperature anomaly, every thermal knot, whispers clues about the dust's journey, from its violent birth in collisions to its slow spiral toward the sun. And as infrared telescopes grow more advanced, we're not just solving the mystery of the zodiacal glow, we're learning to read the solar system's history written in the warmth of a billion scattered grains. If you could reach out and touch the dust that creates the zodiacal lights, what would it feel like? Gritty like beach sand, powdery like charcoal, or something stranger altogether? This isn't just a whimsical question, it's one of the most heated debates in planetary science. While the zodiacal light looks like a uniform glow to our eyes, its dust particles are anything but simple. Some studies argue they're mostly silicates, the same minerals that make up Earth's rocks. Others insist they're carbon-rich, like darkened comet crumbs or cosmic soot. The truth could rewrite our understanding of where this dust comes from and what it's been through on its journey across the solar system. Silicate dust has long been the leading candidate. Spectroscopic studies, which analyze how dust scatters sunlight, often detect telltale signatures of magnesium-rich silicates, minerals commonly found in asteroids and rocky planets. Spacecraft like Cassini and Ulysses have sampled interplanetary dust directly, finding grains with compositions eerily similar to crushed meteorites. If most zodiacal dust shares this pedigree, it would suggest asteroids are the primary suppliers, their collisions grinding rocky fragments into fine powder over billions of years. But there's a wrinkle: some silicate signatures appear too pristine. Freshly shattered asteroid debris should show more weathering from solar radiation and microscopic impacts, yet many dust grains seem oddly unaffected, as if they've been protected somehow. That's where carbon-based theories come in. Certain wavelengths of the zodiacal light reveal a faint but consistent reddening effect, a shift toward longer, redder light that's hallmark of carbon compounds. Think of how charcoal darkens a beach's sand. Carbon absorbs bluer wavelengths, leaving a ruddy tint. The Stardust mission, which captured comet dust in 2004, found grains laced with complex organics and carbon polymers, materials that could explain this spectral reddening. If comets contribute significantly to the zodiacal cloud, their carbon-rich debris might dominate its chemistry. Yet even this explanation has gaps. Carbon-rich dust should be darker, absorbing more sunlight and heating up faster, something infrared telescopes don't always detect. Some regions of the zodiacal cloud radiate far less heat than pure carbon models predict, implying a mix of materials. One provocative study suggests the answer lies in coated grains, silicate cores wrapped in thin carbon shells, like microscopic snowballs rolled in cosmic dirt. These hybrid particles could reconcile conflicting data, offering both silicate-like reflectance and carbon-like spectral features. The most tantalizing clues come from dust's isotopic fingerprints. Some particles trapped in Earth's atmosphere, presumed zodiacal fallout, contain rare isotopes of neon and helium, gases typically found in comet ices. Others show oxygen isotopes matching certain asteroid families. This duality hints that the zodiacal cloud isn't just one type of dust but a cosmic melting pot, blending material from asteroids, comets, and possibly even interstellar space. Unraveling this mystery isn't just academic. Dust composition affects how particles move, cluster, and vanish over time. Silicate grains, being denser, might spiral sunward faster due to Poynting-Robertson drag. Carbon-rich flakes, lighter and puffier, could linger longer or drift on solar winds. Knowing the mix helps us predict the cloud's evolution, and by extension, the solar system's hidden inventory of small bodies. For now, the zodiacal dust keeps its secrets, but upcoming missions like ESA's Comet Interceptor or NASA Destiny Plus aim to sample fresh debris streams, potentially isolating pristine zodiacal particles. Until then, that faint glow in the night sky remains a cosmic Rorschach test seen by all, but revealing its truth only in fragments. Mars' moons, Phobos and Deimos, are often dismissed as mere rubble piles, small, misshapen rocks barely holding together in orbit. But what if these unassuming moons are quietly feeding the solar system's dust cloud, their surfaces shedding material with every micrometeorite strike? The idea isn't as far-fetched as it seems. Phobos, the larger of the two, orbits so close to Mars that it's practically skimming the planet's upper atmosphere. This exposes it to a constant rain of tiny impacts, each collision potentially blasting flecks of its surface into space. Over millennia, that ejected debris could spiral inward toward the Sun, joining the vast reservoir of dust that creates the zodiacal light. The math is compelling. Phobos' surface is pockmarked with craters, some fresh, others ancient, all evidence of a relentless bombardment. Simulations suggest that every impact, even from particles no larger than a grain of sand, could dislodge hundreds of smaller fragments. Unlike Earth's moon, which has enough gravity to pull most ejected material back, Phobos' weak hold, just 1/1000th of Earth's gravity, means much of this debris escapes. Some might fall onto Mars, creating fleeting, high-altitude dust clouds observed by orbiters, but a fraction could slip free entirely, nudged by solar radiation pressure or planetary resonances onto paths that eventually drift into the inner solar system. Deimos, orbiting farther out, faces a different but equally intriguing scenario. Its surface is coated in a thick layer of regolith, loose, dusty material that behaves almost like powder. Thermal stress alone, the constant expansion and contraction from temperature swings, could be enough to loft tiny particles into space. Add in micrometeorite impacts, and Deimos might act like a slow-motion dust fountain, its finer grains easily swept away by the solar wind. Yet not all researchers are convinced. Critics argue that Mars' gravity well would trap most ejected debris long before it could escape into interplanetary space. They point to data from missions like MAVEN, which has detected trace amounts of dust in Mars' orbit, but nothing suggesting a significant outward flow. Others counter that the process could be more subtle, a steady trickle of particles escaping over millions of years, accumulating into a diffuse but measurable contribution. After all, the zodiacal dust cloud isn't built in a day. It's the work of eons of quiet accumulation. The most tantalizing clue might come from composition. Phobos and Deimos are thought to be captured asteroids, rich in carbonaceous material similar to certain meteorite types. If future missions like Japan's Martian Moons e-exploration, MMX, find that their dust matches unexplained signatures in the zodiacal cloud, it could rewrite our understanding of the solar system's dust budget. Even a small contribution from Mars' moons would prove that no source is too insignificant in the grand recycling of cosmic debris. Whether Phobos and Deimos are major players or minor contributors, their potential role reminds us that the zodiacal light isn't just about the dust we see, it's about the countless invisible journeys that brought it there. Every particle has a story, and some of them might begin with a tiny impact on a battered moon, sending a speck of rock on a journey across the solar system, destined one day to catch the sun's light just right. Long before telescopes or satellites, ancient skywatchers recorded a strange glow stretching along the ecliptic, a phenomenon we now recognize as the zodiacal light. But what's striking isn't just that they noticed it, it's how they described it. Babylonian clay tablets from over 2,000 years ago speak of a heavenly river, so vivid it rivaled the Milky Way. Greek astronomers like Eudoxus wrote of a false dawn bright enough to cast faint shadows. Even medieval Arabic scholars, with their meticulously detailed star charts, documented its brilliance, calling it the wolf's tail for the way it seemed to chase the sun. These accounts raise a tantalizing question. Was the zodiacal light once far brighter than it is today? One clue lies in the sheer consistency of these ancient descriptions. Cultures separated by continents and centuries all remarked on the glow's intensity, something modern observers rarely experience unless under pristine, light pollution-free skies. The Roman poet Virgil even referenced it in his works, comparing it to the lingering embers of a dying fire. Such vivid metaphors suggest an atmospheric phenomenon impossible to ignore, not the subtle, elusive glow we strain to see now. Could the dust cloud itself have been denser in antiquity? Some researchers point to a potential culprit, a cataclysmic comet breakup or asteroid collision in the relatively recent cosmic past. Imagine a massive object shattering between Mars and Jupiter, flooding the inner solar system with fresh debris that took centuries to dissipate. Historical records from China and Korea mention guest stars and sudden celestial anomalies around the same time, events we now interpret as supernova or cometary outbursts. Might one of these have been the source of a temporary dust surge? Yet there's another possibility. Our atmosphere has changed. Ancient civilizations thrived during climatic periods like the Roman warm period or the medieval warm optimum, when air clarity and atmospheric conditions might have amplified the zodiacal light's visibility. Dust from volcanic eruptions, which can linger for years in the upper atmosphere, was comparatively sparse during these eras, reducing the haze that now scatters and dims the glow. Even subtle shifts in Earth's axial tilt or orbital eccentricity could have altered how the zodiacal light appeared to observers millennia ago. making it climb higher in the sky or linger longer after sunset. The most controversial theory suggests that human eyes themselves have evolved or devolved in their sensitivity to faint light. Before electric illumination, generations of people lived in near total darkness after sunset, their night vision honed to detect subtler contrast. Modern eyes flooded with artificial light may simply lack the ancestral adaptability to perceive the zodiacal glow as vividly as our predecessors did. It's a haunting thought. The phenomenon hasn't faded, we have. Whatever the truth, these ancient accounts are more than just historical footnotes. They're a window into a time when the night sky was an active participant in human culture, its mysteries woven into mythology, navigation, and timekeeping. The zodiacal light wasn't just a curiosity, it was a celestial marker, a clock, even an omen. And if it truly was brighter then, its gradual dimming echoes a quieter story of how the solar system's slow, silent processes shape not just the heavens but the way we see them. The same solar wind that paints Earth's skies with auroras might also be silently sandblasting the zodiacal dust cloud into oblivion. Picture a relentless stream of charged particles, protons, electrons, even helium nuclei racing outward from the Sun at nearly 1,000,000 miles per hour. When these microscopic bullets collide with interplanetary dust grains, they don't just bounce off. They chip away at their surfaces atom by atom in a process called sputtering. Over centuries, this erosion can whittle down larger particles into smaller ones or even vaporize them entirely, subtly draining the reservoir of dust that creates the zodiacal light. This isn't just theoretical. Spacecraft like NASA, Wind, and ESA solar orbiter have detected unmistakable signs of solar wind weathering on dust particles they've encountered. Some grains show pitted, almost porous surfaces under electron microscopes, their crystalline structures etched by eons of charged particle impacts. Others bear telltale chemical changes, iron atoms knocked loose from silicate lattices, or carbon bonds broken by relentless proton bombardment. These altered grains scatter sunlight differently than pristine ones, potentially explaining why certain regions of the zodiacal glow appear fainter or more diffuse than density alone would predict. The erosion isn't uniform, though. Dust grains rich in metals like iron or nickel withstand solar wind battering better than their carbonaceous cousins, which flake away like graphite under a file. This creates a sorting effect, hardier particles lingering longer in the dust cloud while fragile ones vanish faster. Over time, the zodiacal light's composition might skew toward these metallic survivors, subtly shifting its color and brightness from what ancient observers once saw. Some researchers speculate this could explain historical accounts of a more vivid glow. If the dust cloud once held more pristine, fluffy comet debris, solar wind erosion may have gradually scrubbed it away, leaving behind a leaner, dimmer population of durable grains. But here's the twist: the solar wind doesn't just destroy dust, it can also reshape it. Charged particles can implant hydrogen ions into grain surfaces, creating thin, reactive layers that might catalyze chemical reactions in space. Other grains, bombarded relentlessly, develop electrostatic charges that cause them to clump together or repel one another, altering how they drift through the solar system. In rare cases, sputtering can even liberate atoms from dust surfaces, creating tenuous gas clouds that linger along orbital paths. These secondary effects mean the zodiacal cloud isn't just fading, it's metamorphosing, its particles evolving under the sun's invisible hand. The most fascinating implication lies in timescale. If solar wind erosion is as efficient as some models suggest, the zodiacal dust cloud could be losing mass faster than collisions replenish it. That would mean we're witnessing a slow-motion disappearance, a celestial light show gradually dimming over millennia. Future observations might detect this decline by comparing the zodiacal light's modern brightness to historical records, or by measuring isotopic ratios in dust grains to gauge their exposure ages. Yet for all its destructive power, the solar wind's influence isn't absolute. some dust finds refuge in orbital resonances where gravitational harmonies shield particles from prolonged exposure. Others cluster in temporary eddies or get replenished by fresh cometary debris. The zodiacal light may be fading, but like a candle fighting the wind, it refuses to vanish entirely, a testament to the dynamic balance between creation and destruction that shapes every corner of our solar system. Far beyond Neptune's orbit, in the cold, dark reaches of the solar system, the Kuiper belt holds a treasure trove of icy relics, ancient planetesimals left over from our system's formation. While these frozen worlds seem too distant to influence the delicate zodiacal dust cloud near the Sun, new research suggests they might be stealth contributors to its replenishment. The connection isn't direct, of course. It's a cosmic domino effect spanning billions of miles and countless years. When Kuiper belt objects collide, something they do surprisingly often in their crowded orbital neighborhood, they don't just crack apart like marbles. Their icy surfaces vaporize on impact, releasing plumes of fine dust alongside larger debris. While most of this material remains trapped in the outer solar system by Neptune's gravity, a fraction gets nudged inward over millennia by subtle forces. Solar radiation pressure, gravitational kicks from passing planets, and even the gentle push of the solar wind can set these particles on slow-motion spirals toward the inner solar system. By the time they reach the zodiacal dust cloud's domain, they've been ground down to microscopic sizes by further collisions and erosion, perfect for scattering sunlight into that familiar ethereal glow. But there's another, more exotic way Kuiper belt objects might feed the dust cloud, outgassing. Some of these distant bodies, like the dwarf planet Haumea or the bizarre centaur Chariklo, behave like dormant comets, sporadically venting volatile ices when their orbits bring them closer to the Sun. These outbursts release not just gas but also dust, fine, carbon-rich particles that could eventually migrate inward. The New Horizons mission spotted hints of this process at Pluto, where traces of atmospheric escape and surface sublimation suggest even large Kuiper belt objects might shed material into space. The challenge is proving the connection. Unlike asteroid belt debris, which follows relatively predictable paths, Kuiper belt dust faces a chaotic journey. Neptune's gravity acts like a cosmic sieve, trapping some particles in resonant orbits while flinging others toward the inner solar system. By the time this dust reaches the zodiacal cloud, its chemical signatures, like the ratio of certain isotopes or organic compounds, might be altered beyond recognition. Still, a few tantalizing clues persist. Some models suggest the zodiacal cloud's outer fringes contain more carbon and nitrogen than expected, a possible fingerprint of Kuiper belt ices. Other studies point to rare, hypervolatile minerals in high-altitude dust samples, materials that shouldn't survive the inner solar system's heat unless they originated in the deep freeze beyond Neptune. The most compelling evidence might come from orbital dynamics. The zodiacal dust cloud's density shows faint but measurable fluctuations that align with the predicted timing of major Kuiper belt collisions, as if the inner solar system is feeling the ripples of distant cosmic crashes. If true, this would mean the zodiacal light isn't just a relic of our local neighborhood, it's a living, evolving phenomenon connected to events half a solar system away. Every flicker in its glow could be a message from the frozen edge of our cosmic backyard, written in the language of drifting dust. Whether the Kuiper belt's contribution is minor or major, its potential role reshapes how we see the zodiacal light. No longer just a product of nearby asteroids and comets, it becomes a tapestry woven from the entire solar system's activity, a bridge between the blazing inner planets and the silent, icy realms beyond. And if future missions like the proposed interstellar probe ever sample dust far from the Sun, they might finally catch these far-traveled particles in transit, revealing the invisible highways that connect the solar system's coldest vaults to its most haunting light. Look closely at the zodiacal light through a polarized filter, And you'll notice something strange. It isn't just glowing, it's subtly organized. Unlike sunlight scattered randomly by Earth's atmosphere, this cosmic haze exhibits faint but measurable polarization, with light waves vibrating more in one direction than another. This isn't just a quirky optical effect. It's a fingerprint of the dust grains themselves, revealing their hidden shapes, orientations, and even the invisible forces controlling their dance across the solar system. The key lies in how sunlight interacts with the dust. Imagine tossing a handful of needles into a beam of light. If they're jumbled chaotically, the scattered light will be unpolarized, its waves vibrating in all directions. But if those needles align, say, all pointing east, the light bouncing off them will polarize, favoring waves oscillating perpendicular to their length. That's what's happening in the zodiacal dust cloud, but on a cosmic scale. The grains aren't perfect spheres. Many are likely elongated or flattened, like microscopic splinters or flakes. As sunlight strikes them, these irregular shapes preferentially scatter light in ways that leave it polarized. But here's the mystery. For polarization to occur, the grains can't just be oddly shaped, they need to align. In the vacuum of space, where turbulence is negligible, something must be orienting them. The prime suspect, magnetic fields. The solar system is threaded with weak but pervasive magnetic forces, remnants of the sun's influence and the interstellar medium. Dust grains containing even trace metals, iron, nickel, or magnetite could act like tiny compass needles, turning to match these fields. Solar radiation might amplify the effect, electrically charging the grains and making them more responsive to magnetic whispers. Observational evidence supports this. Spacecraft like the Solar and Heliospheric Observatory, SOHO, have detected polarization patterns in the zodiacal light that shift predictably with the sun's magnetic cycles. During periods of heightened solar activity, when magnetic fields twist and intensify, the polarization becomes more pronounced, as if the dust is snapping into sharper alignment. Other studies suggest the grains might also orient themselves along the solar wind's flow, like weather vanes in a cosmic breeze. Yet not all polarization fits neatly into this picture. Some regions of the zodiacal glow show weaker or more chaotic polarization than models predict, hinting at competing forces at work. Electromagnetic waves from Jupiter's magnetosphere or pressure from sunlight itself could be disrupting the alignment, creating pockets where grains tumble freely. There's even speculation that certain dust populations, perhaps fluffy aggregates of smaller particles, might polarize light differently than compact grains, adding another layer of complexity. The most tantalizing clue comes from comparing the zodiacal light's polarization to that of distant comets. When comets shed dust, their debris often forms long, filamentary trails that polarize sunlight strikingly similarly to the zodiacal glow. This suggests a shared ancestry. Maybe the same processes aligning comet dust also govern the broader cloud. If so, the zodiacal light's polarization isn't just a curiosity. It's a thread tying together the solar system's disparate debris, from icy visitors in the Kuiper belt to the dust underfoot on Mars. What makes this puzzle so compelling isn't just the science, it's what it reveals about the hidden architecture of space. The zodiacal light's polarization is a silent conversation between dust and magnetism, a way to map forces too faint to see directly. Every flicker in that polarized glow is a trace of the solar system's invisible skeleton, written in the language of light and shadow. And as we learn to read it, we're not just understanding a celestial phenomenon, we're deciphering the subtle currents that shape everything from meteor showers to the birth of planets. Close to the sun, where temperatures soar high enough to melt lead, there's a curious void in the zodiacal dust cloud, a region where the delicate particles responsible for the ethereal glow seem to vanish. This dust-free zone defies expectations. If the inner solar system is constantly fed by debris from comets, asteroids, and planetary collisions, why isn't this space choked with drifting fragments? The answer lies in an invisible but ruthless force: the sun's scorching heat. powerful enough to erase dust from existence before it ever has a chance to catch the light. At these extreme distances, mere millions of miles from the sun's surface, temperatures climb to thousands of degrees, enough to vaporize not just ice but even rock and metal. Silicate grains, the building blocks of asteroids, sublimate like dry ice in sunlight, their atoms breaking free and dispersing into the solar wind. Carbon-rich particles fare even worse, crumbling into gas under the relentless thermal assault. This creates an invisible boundary, a sort of cosmic furnace where dust dares not linger for long. Even if fresh debris spirals inward from cooler regions, it rarely survives long enough to contribute to the zodiacal light before meeting its fiery demise. Yet the story isn't quite so simple. Some models predict the dust-free zone should extend much farther out than it does. Observations reveal that dust densities begin plummeting far beyond the region where simple vaporization would take effect, suggesting other mechanisms are at work. One theory points to radiation pressure, the sun's light itself acting like a relentless wind, pushing smaller grains outward before they can drift too close. Larger particles, more resistant to this pressure, might penetrate deeper only to disintegrate at closer ranges. This creates a gradient, not a sharp cutoff, but a gradual thinning of the dust population as the sun's influence grows overwhelming. Another possibility involves electrostatic forces. Intense ultraviolet radiation near the sun can strip electrons from dust grains, leaving them with powerful electric charges. These charged particles then repel one another or get caught in the sun's magnetic field, scattering them like leaves in a storm. Some might even accelerate to escape velocity, flung entirely out of the solar system before they can contribute to the zodiacal cloud. The most startling evidence comes from spacecraft like NASA's Parker Solar Probe, which has flown closer to the sun than any mission before it. Its instruments detect sporadic, hyper-energetic dust impacts, fleeting bursts of particles that shouldn't exist so deep in the vaporization zone. Some researchers speculate these could be dust comets, porous aggregates held together loosely enough to evaporate explosively upon approach. Others wonder if we're seeing the last remnants of larger bodies crumbling in real time, their debris blinking out of existence seconds after detection. What makes this dust-free zone so fascinating isn't just its emptiness, it's what that absence reveals about the solar system's hidden dynamics. The boundary between dust and nothingness is a laboratory for some of the most extreme physics in our cosmic neighborhood, where heat, light, and magnetism conspire to erase matter entirely. And as we study its edges, we're not just solving a puzzle about the zodiacal light, we're glimpsing the sun's power to shape not only what we see in the sky, but what vanishes before our eyes. Most of us picture the zodiacal dust cloud as a slow-moving haze drifting lazily around the sun, but the reality is far more dynamic. These microscopic particles race through space at staggering speeds, some clocking over 70,000 miles per hour as they orbit. That's faster than a bullet, yet their motion isn't chaotic. It follows precise cosmic rhythms dictated by gravity, sunlight, and an invisible force you'd never expect to matter in space, pressure. Not from air or wind, but from light itself. At first glance, orbital speed should be simple. The closer dust is to the sun, the faster it moves, just like Mercury laps Jupiter in their respective races around our star. But zodiacal dust doesn't play by these rules alone. Solar radiation pressure, the faint but relentless push of photons from sunlight, alters trajectories in bizarre ways. Imagine blowing on a dandelion seed floating in midair. Light exerts a similar force on dust grains, especially the smallest ones. Over time, this pressure doesn't just nudge particles, it fundamentally reshapes their orbits. Some grains spiral inward faster than gravity alone would dictate, while others get kicked onto wider, slower paths. The tiniest particles, those thinner than a wavelength of light, can even be pushed outward entirely, creating a slow-motion fountain of debris fleeing the inner solar system. This explains one of the zodiacal light's great oddities, its asymmetrical glow. The dust cloud isn't uniform because particles at different distances move at different speeds, their orbits warped by radiation pressure. Near Earth's orbit, most dust streaks along at about 45,000 miles per hour, but deeper in, closer to Venus, speeds spike to nearly 90,000. These velocity gradients create density ripples like traffic jams in space where particles pile up, amplifying the zodiacal light in certain regions while thinning it in others. The most mind-bending twist, some dust moves backward. While rare, a fraction of particles, usually those recently shed by comets on retrograde orbits, circle the Sun in the opposite direction of the planets. When these mavericks collide with mainstream dust, their head-on impacts vaporize both grains in flashes too faint to see but detectable by sensitive instruments. These collisions leave behind chemical signatures that linger in the zodiacal cloud like cosmic skid marks hinting at past violence. Tracking these speeds isn't just academic. The dust's velocity profile acts like a forensic record, revealing where particles originated and what forces shaped their journey. Fast-moving grains near the Sun likely spiraled in from the asteroid belt, while slower outliers might be interstellar hitchhikers or comet debris still adjusting to solar orbit. Future missions could map these speed zones in detail, turning the zodiacal light into a cosmic speedometer, one that measures not just dust, but the hidden currents of our solar system's rivers of rubble. During the Apollo missions, astronauts reported something unexpected, a faint glow along the Moon's horizon just before sunrise. Not the soft blue of Earth's dawn, but an eerie, almost electric luminescence stretching above the barren landscape. At the time, some scientists speculated this wasn't just scattered sunlight, it could be evidence of levitating lunar dust, tiny particles hovering above the surface, backlit by the approaching Sun. And if dust could escape the Moon's gravity, even briefly, might it also drift into space, adding to the zodiacal cloud? For decades, this tantalizing idea lingered, that our own Moon might be stealthily feeding the solar system's dust reservoir, its microscopic ejecta blending into the cosmic haze. The theory wasn't baseless. The Moon's surface is a relentless battleground, bombarded by micrometeorites that kick up countless dust grains with every impact. Unlike Earth, where atmosphere quickly slows and traps such debris, the Moon's vacuum offers no resistance. Simulations suggested that a fraction of these particles, especially those struck by high-energy impacts near the terminator, the line between lunar day and night, could reach escape velocity. Once free, solar radiation pressure might nudge them into stable orbits around the Sun, where they'd mingle with the zodiacal dust. Apollo-era experiments even claimed tentative evidence, faint spikes in dust detector readings during sunrise terminator crossings, as if instruments were catching whiffs of this escaping haze. But modern research paints a very different picture. Recent studies using ultra-sensitive detectors aboard NASA's spacecraft, the Lunar Atmosphere and Dust Environment Explorer, found no trace of a permanent high-altitude dust layer. Instead, the Moon's exosphere is far cleaner than expected, with dust densities thousands of times lower than Apollo-era estimates. Any particles managing to escape lunar gravity would be so sparse, they'd contribute less than a fraction of a percent to the zodiacal cloud's total mass. The faint horizon glow astronauts observed, it's now attributed to an entirely different phenomenon, electrostatically charged dust grains, yes, but ones merely hopping centimeters above the surface before falling back, like tiny cosmic jumping beans trapped in place by the Moon's gravity. The real nail in the coffin comes from composition analysis. Lunar dust is chemically distinct from typical zodiacal particles, packed with minerals like anorthosite and regolithic glass forged by eons of meteorite impacts. If the Moon were a major contributor, spectrographs would detect its signature in the zodiacal light spectrum. Yet outside a few disputed anomalies, no such matches exist. Even the isotopes don't align. Lunar oxygen ratios, imprinted by the Moon's unique formation history, are virtually absent from sampled interplanetary dust. So why the disconnect between past and present data? One compelling explanation points to the Apollo instruments themselves. Early detectors, revolutionary for their time, were prone to false positives. Electrical noise, cosmic rays, even outgassing from the lunar module could mimic dust signals. Modern tools, shielded and calibrated to weed out interference, reveal a quieter reality. That's not to say the Moon contributes nothing. Micrometeorite impacts do launch a handful of grains into space annually, and over billions of years this trickle might add up. But in the grand ledger of the zodiacal cloud, the Moon's line item is negligible, a rounding error compared to the flood of debris from comets and asteroids. The lunar dust controversy isn't just a scientific correction, it's a lesson in how easily cosmic mysteries can morph under sharper scrutiny. What once seemed like a bold connection between Moon and zodiacal light now stands as a cautionary tale. Sometimes the most poetic explanations are the ones the universe reserves for fiction. Yet the Moon hasn't lost all its intrigue. Those electrostatic hops, while too feeble to escape, might still sculpt the lunar landscape over millennia, etching patterns we've yet to fully understand. And who knows, perhaps future lunar bases, with their digging and drilling, will send up more dust than nature ever did, making humans, not the Moon itself, the unexpected contributors to that age-old glow in the sky. Deep in the void between planets, an invisible rain falls, cosmic rays, high-energy particles racing across the galaxy at near light speed. When these interstellar bullets strike the delicate grains of the zodiacal dust cloud, they don't just pass through, they transform them. Each collision can strip away electrons, leaving behind electrically charged husks, dust grains turned into celestial ions. This invisible process might seem like a minor detail, but it could hold the key to some of the zodiacal light's most puzzling behaviors, from unexpected brightness fluctuations to the way certain dust populations mysteriously cluster or disperse. Cosmic rays originate from some of the universe's most violent events: supernova explosions, pulsar jets, even the supermassive black holes at galactic centers. By the time they reach our solar system, they've traveled for millions of years, carrying enough energy to punch through solid rock. When one slams into a zodiacal dust grain, the impact is apocalyptic on a microscopic scale. The grain's surface erupts in a tiny burst of secondary particles, while the loss of electrons leaves it positively charged. Suddenly, what was once an inert speck of rock or ice becomes a player in an electromagnetic dance, sensitive to forces it would have ignored before. This ionization has startling consequences. Charged dust grains don't just drift passively, they respond to magnetic fields weaving through the solar system. Some might align like iron filings near a magnet, amplifying the zodiacal light's polarization in ways we've only begun to measure. Others could get caught in solar wind currents, accelerated to higher orbits or flung inward toward the sun. There's even evidence that highly charged grains repel one another, preventing them from clumping and explaining why some regions of the dust cloud appear smoother than collision models predict. The most compelling clues come from solar cycles. During periods of high solar activity, the sun's magnetic field strengthens, shielding the inner solar system from cosmic rays. When researchers compared decades of zodiacal light observations with cosmic ray flux data, they found a curious pattern. The glow's intensity dipped slightly during solar maxima, as if the dust itself dimmed without the constant bombardment of ionizing particles. This suggests cosmic rays don't just alter dust dynamics, they might actively energize the zodiacal light, like invisible hands tuning its brightness. Yet the story isn't so straightforward. Some cosmic rays are so powerful they don't just ionize dust, they annihilate it. A single high-energy particle can vaporize a grain entirely, turning it into a puff of plasma. Others might shatter larger particles into smaller, more volatile fragments. This raises a provocative question. Is cosmic ray bombardment slowly eroding the zodiacal dust cloud, or is it somehow replenishing it by breaking down bigger debris into the fine particles that scatter sunlight so efficiently? The answers might lie in laboratory experiments that recreate these extreme conditions. Using particle accelerators, scientists have zapped synthetic dust grains with proton beams, simulating cosmic ray impacts. The results are mesmerizing. Some grains develop fractal-like cracks, their surfaces etched with microscopic canyons. Others eject spiral tendrils of vaporized material like tiny comets. These damaged grains scatter light differently than pristine ones, potentially explaining why the zodiacal glow's spectrum doesn't quite match any known asteroid or comet type. What's truly astonishing is the scale. Astronomers estimate that every second, trillions of cosmic rays pierce the zodiacal cloud, a non-stop hailstorm lasting billions of years. Over epochs, this relentless assault could have fundamentally reshaped the dust population, winnowing fragile grains and leaving behind a cosmic ray-resistant residue. If true, the zodiacal light we see today might be the hardened survivor of an ancient, more diverse dust cloud, one whose original brilliance and composition we can only reconstruct through these subtle, ionization-shaped clues. So the next time you glimpse that faint glow on the horizon, remember, you're not just seeing sunlight on dust, you're witnessing the aftermath of a galactic shooting range where particles from across the universe leave their fingerprints on the solar system's most delicate structures. And somewhere in that interplay of light, charge, and destruction lies a story still being written one cosmic ray at a time. Humanity's footprint in space extends far beyond the satellites orbiting Earth. Our discarded rocket stages, shards of debris, and even flecks of paint from decades of spaceflight now drift through the solar system. Could this artificial junk be mingling with the natural dust that creates the zodiacal light? At first glance, the idea seems far-fetched. The zodiacal cloud spans millions of miles, fed by asteroids and comets that have been crumbling for billions of years. Compared to that vastness, a few thousand tons of human-made debris should be negligible, but dig deeper and the math gets unsettling. Consider this: every satellite launch kicks more than just a spacecraft into orbit. Flakes of insulation, frozen fuel residues, and even microscopic fragments from thruster plumes escape into the void. Over time, solar radiation and micrometeorite impacts grind down defunct satellites into ever smaller pieces. The European Space Agency estimates there are over 100 million artificial particles larger than a millimeter in Earth's vicinity alone, many on trajectories that eventually intersect the inner solar system. While most burn up in Earth's atmosphere, a fraction escape into heliocentric orbits, where solar radiation pressure can nudge them toward the zodiacal dust cloud's domain. The real wild card is scale. Unlike natural dust, which tends to follow predictable orbital planes, space debris is chaotic. Old rocket boosters tumble in erratic orbits, shedding material as they go. Collisions between dead satellites, like the infamous 2009 Iridium Cosmos crash, create sudden bursts of fragments that disperse like shrapnel. Computer models suggest some of this debris could spiral inward over centuries, blending with the zodiacal cloud, the telltale sign: unusual spectral signatures. Aluminum, titanium, and composite materials from satellites reflect sunlight differently than asteroid-derived silicates or comet-borne organics. If future telescopes detect mismatched glints in the zodiacal light's glow, it could be the fingerprint of human activity. Yet skeptics argue that even our messiest spacefaring efforts pale against nature's output. A single moderately active comet like Encke sheds thousands of tons of dust per orbit, dwarfing humanity's total contribution. And while artificial debris might briefly spike near Earth, Jupiter's gravity acts like a cosmic vacuum, sweeping most stray particles away before they reach the inner solar system. Even if some human-made dust lingers, it's likely diluted to irrelevance. the debate takes a darker turn when considering long-term trends. With mega-constellations like Starlink launching tens of thousands of satellites and plans for lunar industrialization gaining traction, our debris output could skyrocket. A study from the National Research Council warned that within a few centuries, space junk might rival natural micrometeoroid fluxes in low Earth orbit. If that pollution leaks into the zodiacal cloud, future astronomers might find their view of the solar system's pristine dust forever altered. For now, the verdict is hazy. No direct evidence ties space debris to zodiacal light pollution, but absence of proof isn't proof of absence. As detection methods improve, scientists might finally spot the glint of a stray satellite fragment in that ancient glow. Until then, the possibility lingers like a whisper in the cosmic dark. Even our grandest celestial mysteries might not escape the touch of human hands. The zodiacal light has graced our skies for billions of years, but like everything in the cosmos, it won't last forever. The delicate balance feeding this ethereal glow is already shifting, quietly transforming in ways that could one day render it unrecognizable. Picture the solar system 10 million years from now. Comets, the icy wanderers that replenish the dust cloud, may have dwindled to a handful as the Oort cloud's reservoir slowly depletes. Jupiter's gravity, ever the cosmic gatekeeper, could have nudged the asteroid belt into a quieter era, reducing collisions that once sprayed fresh debris into the void. Meanwhile, the sun itself grows brighter with age, its intensifying radiation vaporizing dust grains faster than ever before. The result, a zodiacal light that grows fainter with each passing epoch, its glow fading like a dying ember. Yet the future isn't just a story of loss. Cataclysms could rewrite the script overnight. Imagine a massive asteroid collision in the distant Kuiper belt, scattering enough icy rubble to flood the inner solar system with fresh dust. Or a rogue star passing uncomfortably close, disturbing the Oort cloud and sending a swarm of comets spiraling inward, a celestial snowstorm that revitalizes the zodiacal cloud for millennia. Even human activity might leave a mark. Future space mining could churn up asteroid debris, while mega-engineering projects like solar shades or orbital habitats might inadvertently seed the cloud with reflective particulates. The zodiacal light of tomorrow could bear the fingerprints of civilizations not yet born. The most startling possibility lies beyond our solar system. As the Milky Way and Andromeda galaxies inch toward collision in 4 billion years, the resulting chaos could fling stars and their planetary systems into strange new orbits. A passing star might steal our sun's outer comets, starving the zodiacal cloud, or it could gift us fresh reservoirs of icy bodies. Gravitational tides might even compress the dust into luminous rings, turning today's subtle glow into a dazzling celestial belt visible from worlds light years away. What's certain is this: the zodiacal light is a fleeting phenomenon on cosmic timescales. The same forces that birthed it, the grinding of asteroids, the size of dying comets, the silent pull of gravity, will one day dismantle its delicate architecture. But in its impermanence lies a lesson. The universe is never static, and even its most haunting beauties are just temporary signatures of deeper, grander cycles. For now, we're lucky enough to stand in the brief window when sunlight still catches the dust just right, painting the dawn with echoes of creation itself. Among the many theories surrounding the zodiacal light, one of the most outlandish suggests it isn't a natural phenomenon at all, but the glow of alien megastructures harvesting energy from our sun. This idea, popularized by fringe online communities, hinges on the notion that the light's faint, diffuse radiance could be artificial, perhaps from vast solar panels or Dyson swarms built by an advanced civilization. While the concept sparks the imagination, the reality is far less sensational and far more fascinating. Science offers clear, evidence-based explanations that leave little room for extraterrestrial engineering, no matter how compelling the myth may seem. The megastructure theory first gained traction when astronomers observed unusual light patterns around distant stars, prompting wild speculation about alien technology. Some theorists then retroactively applied this idea to our own solar system, suggesting the zodiacal light might be a local example of such structures. But the comparison collapses under scrutiny. Distant starlight anomalies involve irregular, unpredictable dimming, nothing like the zodiacal light's consistent, predictable glow tied to the ecliptic plane. Telescopes have mapped this dust in infrared, revealing its temperature and distribution to perfectly match natural interplanetary debris, not the rigid geometry of artificial constructs. The composition of the dust itself is another nail in the coffin. Spectroscopic analysis shows it's made of silicates, carbon compounds, and other minerals found in asteroids and comets, materials you'd expect from cosmic collisions, not precision manufacturing. If aliens were building megastructures, why would they use the same gritty, irregular particles that litter our asteroid belt? Even more damning is the way the dust behaves. Solar radiation pressure and gravity sculpt the zodiacal cloud into smooth gradients and resonant bands patterns dictated by physics, not design. Artificial collectors would need stabilization against such forces, creating telltale deviations in orbital motion that simply aren't observed. Then there's the sheer inefficiency of the idea. The zodiacal light is faint because it's sunlight scattered by sparse, tiny grains, not concentrated or harvested. A civilization advanced enough to build a Dyson swarm would capture energy far more effectively, likely rendering their structures invisible to our eyes as they'd absorb, not reflect, sunlight. Instead, we see precisely the opposite, a glow that aligns perfectly with what natural dust ought to do. Perhaps the most compelling counterargument comes from history. Ancient Babylonian, Greek, and Arabic astronomers documented the zodiacal light millennia before modern technology. If it were an alien megastructure, its brightness would have changed over centuries as the hypothetical construct expanded or degraded. Yet historical descriptions match today's observations, suggesting a phenomenon as stable as the solar system itself. The real wonder isn't in imagining extraterrestrial handiwork, it's in recognizing how nature, left to its own devices, crafts something so hauntingly beautiful from the rubble of cosmic collisions. That's not to dismiss the value of speculative thinking. The megastructure myth, however far-fetched, reflects humanity's drive to seek meaning in the unknown. But science thrives on evidence, and the evidence here is clear. The zodiacal light is a testament to the solar system's untidy, glorious chaos, not the signature of a hidden civilization. The truth may lack the thrill of alien engineers, but it offers something richer, a glimpse into the dynamic processes that shape all planetary systems, a reminder that sometimes reality outshines even our wildest fiction. After centuries of study, the zodiacal light still guards its deepest secrets, leaving scientists grappling with questions that defy easy answers. Perhaps the greatest mystery revolves around the dust's true origins. While asteroids and comets are the leading suspects, their debris doesn't quite match all the observed properties. Some dust particles show chemical signatures unlike anything found in known meteorites, hinting at exotic sources we've yet to identify. Could there be undiscovered asteroid families with unique compositions? Might interstellar visitors' dust grains born around other stars be mixing into our solar system's cloud? Or could processes we don't fully understand, like vaporization and recondensation in space, be transforming ordinary particles into something unrecognizable? The distribution patterns present another enigma. Despite sophisticated modeling, the dust cloud's density fluctuations don't always align with predictions. Certain regions appear inexplicably thick, as if hidden forces are corralling particles together. Elsewhere, unexpected voids yawn open, areas where dust should accumulate but doesn't. Some researchers speculate these gaps might reveal the gravitational fingerprints of as yet undiscovered planets, their subtle tugs clearing paths through the debris. Others wonder if electrostatic forces or solar magnetic fields could be shaping the cloud in ways we're only beginning to comprehend. Perhaps most perplexing is the dust's longevity. Given the constant losses to solar vaporization and pointing Robertson drag, the zodiacal cloud should have depleted long ago unless replenished by a vigorous source. Yet current estimates of comet and asteroid activity fall short of explaining the observed replenishment rate. This discrepancy has led to daring hypotheses. Could there be massive, unseen collisions in the distant Kuiper belt generating fresh dust? Might the Oort cloud be leaking comets into the inner solar system at higher rates than we've calculated? Or could an entirely different mechanism, like the slow disintegration of dark, carbon-rich bodies, be steadily feeding the cloud? The zodiacal light's polarization adds another layer of intrigue. While some alignment with the solar magnetic field is expected, certain measurements show patterns that current theories struggle to explain. Could this hint at exotic particle shapes, perhaps fractal-like aggregates formed in microgravity, or novel electromagnetic interactions in the near vacuum of space? Even the color variations resist simple interpretation, their subtle shifts possibly encoding information about the dust's thermal history and formation processes. These unanswered questions aren't just academic, they're portals to deeper truths about our solar system's evolution. Every unexplained facet of the zodiacal light reflects gaps in our understanding of planetary formation, cosmic collisions, and the intricate interplay of forces that govern seemingly empty space. Solving these puzzles might require revolutionary tools, space-based dust analyzers capable of capturing individual grains, or telescopes sensitive enough to map the cloud structure in 3 dimensions. What makes these mysteries so compelling is their accessibility. You don't need a billion-dollar observatory to contribute. Your own observations under dark skies could still reveal undocumented fluctuations in the zodiacal light's brightness or extent. Citizen scientists have helped track meteor showers and comet activity for decades. Who's to say the next crucial clue about our solar system's dusty veil won't come from an attentive stargazer's notebook? The zodiacal light reminds us that even familiar skies hold profound secrets, waiting for curious minds to unravel them. Its lingering questions aren't dead ends, they're invitations to look deeper, think harder, and keep wondering about the subtle glow that has captivated humans since we first gazed upward. In that sense, the greatest mystery may be why we ever stopped questioning it at all. From the eerie asymmetry of the zodiacal dust cloud to the baffling gaps where gravity carves voids in nothingness, each of these 25 mysteries peels back another layer of the solar system's hidden story. We've traveled from the scorching inner sanctum near the sun, where dust vanishes into vapor, to the frozen edges of the Kuiper belt, where icy debris might quietly feed the glow. Along the way, we've seen how Jupiter acts as a cosmic sculptor, how ancient civilizations witnessed a far brighter sky, and how even the faintest polarization of light reveals the invisible hand of magnetism shaping particles smaller than a grain of sand. Every unanswered question, whether about the dust's missing mass, its shifting colors, or its potential whispers of undiscovered worlds, isn't just a puzzle. It's an invitation to marvel at how much we still don't know about the space we call home. This isn't just science, it's a reminder that the universe is stranger and more wondrous than we often assume. The same delicate glow that inspired Babylonian poets and Greek astronomers still holds secrets today, challenging our brightest minds with every new discovery. And here's the beautiful part: you don't need a telescope to be part of the mystery. On your next clear night, long after sunset or just before dawn, step outside away from city lights. Let your eyes adjust. That faint, ghostly triangle rising from the horizon. It might be the zodiacal light, sunlight catching on cosmic dust that's traveled farther and endured longer than you can imagine. And if you're lucky enough to spot it, you're not just seeing a pretty glow. You're witnessing a conversation between starlight and the debris of creation itself, a whisper from the solar system's untold history. So tell us, have you ever seen the zodiacal light? Share your stories in the comments. And if you've enjoyed this journey through the cosmos' quietest marvel, don't forget to subscribe. The universe is full of mysteries, and together we'll keep uncovering them, one shimmering question at a time.